Alright, so welcome to one of the toughest lessons in Math 2 in my opinion. What's going to happen is there are some things that are kind of strange about this. Like if you have exactly the same exponent on both bases, you can actually multiply those bases together. So that'd be 2 times 3, which would be 6 to the third power, then to the negative 1/3 power. And then you could actually raise a power by multiplying the powers together. So 3 times negative 1/3 would be negative 1. And then anytime you got a negative exponent, you move that to the denominator. So 1 over 6 to the first power would actually be my answer on number 1. So I'm going to be flying through about 12 problems here, showing you how to do these. Next up, I would write that 10 is to the first power there. And so I would actually combine the 10s as 10 to the 1 minus negative 4/5. I cannot write 10 as like 2 to the something power. It just doesn't work out too well. I'm going to write that as 10 to the, I'm going to change 1 to 5/5. And that's going to be plus 4/5. And that's going to be 10 to the 9/5. I cannot simplify this anymore. Even though 10's composite, it's 2 times 5, which doesn't have any repeating powers. So that's good right there. Moving on to the next. Again, I have an exponent on 5 on both of these. I'm actually just going to go ahead and divide those. So that's going to be 13 to the 5th power. I did 52 divided by 4 is 13. And then this will be to the 1/6. I will multiply 5 and 1/6 together to get 13 to the 5/6 power. 13 is prime, so I'm actually going to stop right there on this problem. Realized I was going off the screen a little bit. Alright, number 4. This is where things kind of really start to get difficult a lot. This is, by the way, in your work text on page 82. I forgot to mention that at the beginning. So right here, I'm actually going to be changing 27 to 3 to the 3rd power. So I still have 3 to the 1/3 as my first term, times, I'm going to rewrite 27 as being 3 to the 3rd power, and that will still be to the 2/3. Just a nice first step to do. You could also do it for 8, so 8 would be 2 to the 3rd, 2 times 2 times 2, and it will be to the 4/3. Now I'll start simplifying everything down. 3 to the 3rd to the 2/3, 3 times 2/3 would be 2. So I'm going to have 3 to the 1/3 times 3 to the 2nd now as my numerator. On my denominator, 2 will be to the 3 times 4/3. The 3's would cancel. You're left with 4. Now I can actually add these two exponents on the numerator since each base was 3. So that would be 3 to the 1/3 plus 6/3 would be 7/3. 2 to the 4th power can be simplified. That's going to be 16. And that's actually a good answer right here. That's as far as you can take it. Alright, looking at the perimeter and area on number 5. For perimeter, you just do 4 times whatever the side length is for a square. So 4 times 10x to the 1/4 power will be what I do here. So that's going to be 40x to the 1/4 as my perimeter. For area, I'll do a side squared. Since it's a square, you're going to square the length of a side to get your area. So 10x to the 1/4 power is going to get squared. You are squaring both the 10 and the x to the 1/4. 10 was to the first power. 1 times 2 was 2. Now 10 squared is going to be 100. Now x will be to the 2/4 power, which we reduce to 1/2. So 100x to the 1/2. Alright, as a quick reminder, I am instructing this video without a calculator, but you are more than welcome to try typing these in the calculator because when you get rational answers, they would work. Anyways, when I'm multiplying roots with the same index, that's possible. So this will be the 6th root of 25 times 625. That ends up being 15,625. Before hitting that panic button, though, that is a 6th power itself because that represents 5 being raised to the 6th power. The 6th root and the 6th power would cancel, and you would have 5 as your answer. So that really helps us on a problem like number 7. 343 is actually divisible by 7. So 343 divided by 7 would be 49. So this is the square root of 49, and that's easy enough. That's 7. So we're getting nice, pleasant, rational answers here. Now that's going to be a little bit different on number 8, but while you can't divide 25 by 2, I could divide the 10 by 2 pretty easy. So I'm going to have the cube root of 25 times the cube root of 10 divided by 2 will be 5. All right, made it a little bit better. The cube root would now be of 25 times 5, which is 125, which is actually something I can cube root since that's 5 cubed, and cube root and cube would cancel. So 5 is your answer. So all three of those could have been done in your calculator. All of a sudden, number 9 is something that's irrational. So your initial impression might be, I can't do anything with it. But in fact, if you look at the prime factor tree for 384, since it's even, I know it's divisible by 2, which will multiply with 192. And you just keep on working this prime factor tree really quick. So 2 times 96, I am using a calculator off to the side. I'm not that great at math. 2 times 48 is 96. 2 times 24. 4 times 6, which is 2 times 2, and 2 times 3. So now what I know is the 7th root would be of 2 to the 1, 2, 3, 4, 5, 6, 7th power. 2 to the 7th power times 3 is only to the 1st power. Now notice that I don't make any mention of these composite numbers along the way because they were composite. I'm only interested in the primes. Now the 7th root of 2 to the 7th is really easy. That's just 2 to the 1st. And it will be multiplying the 7th root of 3. And that's actually my final answer there. Sorry that I didn't show all of that work there. I just realized that might have been off the screen. But there was the rest of my prime factor tree. So 1, 2, 3, 4, 5, 6, 7th power is what my 2 is being raised to. So number 10 here, what's going to happen is I cannot have an irrational denominator. So this is the cube root of 5 being divided by the cube root of 9. 5 over 9 won't simplify, so that doesn't help me. What I'm going to do is I'm going to make this a perfect cube on the denominator that I can cube root. So since this is 3 squared, I'm going to make it 3 cubed, which would be 27. So I'm going to multiply the top and bottom by the cube root of 3 in order to make that happen. So in my numerator, I'm now going to have the cube root of 15, cube root of 5 times cube root of 3, over the cube root of 27. The reason why that's super helpful to do that step is because now I can actually take the cube root of 27, which will simply be 3 on the denominator, and that's a nice rational denominator. And on the numerator, I'd have cube root of 15. And you'd be finished right here. Moving on to number 11 and 12, they're really kind of the same problem, so I'm actually just going to do 11 for the purpose of the video. The root is the problem. It's irrational. So how do you get rid of it? You do multiply the top and bottom by something, but it's going to be what's called the conjugate of that binomial. So the conjugate would be 4 plus the square root of 5. If I multiply by that on top and bottom, it's going to make that denominator rational all of a sudden. So let's go ahead and distribute the 1 on top. 1 times 4 is 4. 1 times root 5 plus 1 root 5. That was actually very easy. On the denominator, this is now a difference of 2 squares. So it's going to, if you multiplied it out, it would go to a squared minus b squared. The a is 4. So 4 squared is 16 minus b is root 5. And when I square root 5, I get 5. Now I just need to make 16 minus 5, 11. The numerator is actually just going to stay irrational, 4 plus root 5, and I'm done. All right, there's probably going to be a ton of questions on this, so you definitely need to be coming to my focus for help. Please let me know what I can do for you in regards to this stuff. Thanks.